let's start with section 7.8, which is on improper integrals. Now when it comes to improper integrals, there we have two types, type 1 and type 2. So to explain what these types means, let me start with an example, right? So now I'm going to explain what type 1 improper integrals are, and later on we'll go to type 2. Okay, right. So for type 1, first of all we'll consider a very simple function, which is fx is equal to 2. This is a constant function. So if we draw the graph of this constant function, it will be like this. It's a straight line parallel to the x-axis that goes through 0, 2 point in the y-axis, right? So now how about the area under the graph? Now let's say, for example, if we consider the integral from 0 to 1, how can we represent it in the diagram? This is simply the area in between 0 and 1 of this graph, right? So this will be the area, right? And how about integral of 0 to 2? Then that will be the area from 0 to 2, right? Likewise, what if I write it as 0 to t of fx, where t is a number? So accordingly, this represents, now let's say if t is a, we'll consider t as a positive number. Okay, so this integral will represent the area from 0 to t of our given function, where in this case the given function is fx is equal to 2. So this integral will represent the area from 0 to t, where t is a positive number. So it will be located to the right of 0, right? Okay, I mean in this side. Okay, now how to compute? Let's try to compute this integral. So the integral of fx dx means the integral of 2 dx, right? And that means 2x, and if we have lower limit and upper limit, then it will be 2 times t. Okay, so even without completing the simplifying the integral, we just by looking at this diagram we can see that you have a rectangle. So the area of the rectangle is length times breadth, right, which is 2t. Okay, right. Now when it comes to this number t, you can see this t can be large as much as we need, right? In other words, this t can be extended to infinity. What do we mean by that? So if I extend t to infinity, in other words, it means we are finding the area of this under this function starting from 0, and it will go like infinitely to the right hand side. Okay, so it will continue forever, and we need to find the area of that region. Okay, so can you make a guess of that, of the area in that region? See, now if this is only 1, the area will be 1 times 2, just by considering the rectangle, which is 2. And if it is, let's say 3, it will be 3 times 2, which is 6. See, now when t increases, the area will also increase, and to find the exact value, what we can do is we can just now, in other words, to find the exact value for this integral expression, what we can do is we can visualize it as a limit problem, right, where t represents the upper limit and we compute the integral of the same function with the given lower limit and t as the upper limit. So, and for this particular example, we can see that the answer for fx, the integral of x, where we have 0 and t as the upper and lower limits, we have the answer as t goes to infinity of 2t, which is equal to infinity, right? So now here what I want to say is that if we have an integral with infinity as the upper limit, you can visualize the same problem as a limit of a certain integral. And how do we relate the limit with this infinite integral? We just use t as the infinite position and just take the limit where t goes to infinity. And how do we compute this limit problem? We just consider this integral as a definite integral and then compute its answer just by considering t as a number, and then we directly compute the limit of that number. Okay, right, and then we'll take another example. Now we'll consider the function fx is equal to 1 over x squared. Then to find the limit with infinity as the upper limit, we can follow the same procedure, right? We can consider it as a limit problem where we have the function as our here you should have t, okay, and we should consider the lower limit as 1, okay, because at 0 this function is not defined. And yeah, so basically what we do is we consider the graph of this function and then take the area starting from 1 and towards infinity, right? So we just compute the area under this graph starting with 1. That's why we choose 1 as the lower limit, right? So now just see, even though we are computing an infinite area of this graph, by solving this integral as I explained before, that is by considering t as a number and just taking the limit, we can see that the answer will be a finite value, right? Now here we considered an infinite area under this graph and the answer was infinity. But here also we considered an infinite an area of an infinite region, right? Starting at 1, we got the area of this infinite region, but the answer was equal to 1, right? In other words, although this region is infinite, its area is a finite value. This is kind of a interesting result, right? Because now when you say an infinite area, it's somewhat like intuitively you might feel that the area should also be infinity. But see, mathematically it is not true, right? That's what we have shown here. Okay, so although you take the area of an infinite region, it may or may not be infinity. Okay, right. So this is the property addressed by the type 1 improper integrals, right? Now I am going to tell you the exact definition of the type 1 improper integrals. So when it comes to the definition, the type 1 refers to the infinity at the limit point, right? If you have infinity as an upper limit or as a lower limit, we consider that integral as a improper integral type 1, right? And how do we compute the compute such an integral? We just consider the limit of this definite integrals. Now here this infinity can also take place at the lower limit as well, right? And another thing, this finite number need not to be 0 always. Remember, now in that previous two examples, the first one I considered it from 0 to infinity, and the next one I considered from 1 to infinity, right? This starting point is like, for this starting point, it is not a must to have 0 all the time. It can be any value, right? It can even start from a negative number also, right? And another thing is that you can even consider the negative infinity. That means we can consider the area towards this negative side as well, right? But for all these two parts, there is one more thing that should satisfy, which is, now when we are taking this infinity, now let's take the first part, that is the positive infinity case. When you are taking the positive infinity, this integral, when you take the finite integral, this one should always exist, right? In other words, like if we take any finite number, this area will be a finite value. Okay, that property should also satisfy to define these equations, right? So simply, if you say improper integral of type 1, that means we will have infinity in the upper limit or we will have infinity in the lower limit. But if you have infinity in the lower limit, that should be negative infinity. Okay, and there's one more thing. Now you saw in the examples, the first one had infinity as the answer, right? And the second one got a finite value as the answer, right? See, here we have infinity and here we have a finite value. So depending on the finite or the infinite nature of this answer, we categorize these integrals as a convergent integral or a divergent integral, right? So it's kind of obvious by the name itself. We say convergent if this limit exists in the sense finitely exist, right? In other words, if this limit is finite, we say that the integral, the improper integral, is convergent. And if it is not finite, we say the improper integral is divergent. And now it is true for both infinity in the upper limit and negative infinity in the lower limit, right? Now in the example that I did, both has infinity as the lower limit, the upper limit, but it is the same definition goes where even if we have negative infinity at the lower limit, right? And then there is another additional part for this improper integral type 1. Okay, so now up to this point I said like we consider an integral to be an improper integral if we have infinity as a lower or upper limit, and then it converges if this limit value exists finitely, and it diverges if it doesn't finitely exist, right? Now if both a infinity and negative infinity a exist finitely, in other words, if both these integrals converge, or if they are convergent, then we define this integral. See, now here we have the lower limit and upper limit, like we have infinities in both lower and upper limits. So we consider this one as starting from negative infinity to a fx plus a to infinity fx, right? So now if we visualize this with the diagram, we can say if we have this as the function, here what we do is the left hand side represents the area of this function, this is fx, starting from negative infinity and goes towards positive infinity. Okay, so this represents the area throughout the region of x. Okay, and these two will represent area like this. Now this value a need not to be 0 all the time. It can either be 0 or you can even choose any number, right? Like a can even be a negative number. Let's take negative 10. So this equation will represent that the same area throughout this region can be obtained by computing this area separately and adding that area to the one you have in the left hand side, right? So that's the kind of the meaning in this equation, right? The area throughout this region is the same as the area of the left hand side and area from the right hand side starting from a random point. Okay, but to define this equation, or for this equation to make sense, both these integrals should converge. That's important. Okay, now see, in the very first example that I told, this integral 0 to infinity integral is not convergent because the answer is infinity. So therefore we cannot write an equation similar to the one I wrote at the end, right? So for that example where fx is equal to 2, this equation doesn't make any sense because this integral is not convergent, right? And in that first example we have a as 0. So our starting point is 0, but it is not a must to start from 0 all the time. Okay, so as a summary, what do we mean by an improper integral of type A? That's basically an integral that has got infinity at the upper limit or infinity at the lower limit. And if you are taking the infinity at the lower limit, you should have negative infinity. And we defined convergence for these types of integrals, right? And what do we mean by convergent? If we have infinity in the upper limit and a number in the lower limit, we define the convergence as the limit of this one when t goes to infinity starting from a to t, right? If this value is finite, we said the improper integral is convergent. And for this one, when you have negative infinity at the bottom and a number in the top, then we define the limit as t goes to negative infinity from t to a. And if this is finite, we say the improper integral is convergent. And if both these integrals are convergent with the common finite point, that means this one and this one, if both these are convergent, then we can derive our equation for the infinite region starting from negative infinity and going up to the positive infinity. And we have this equation as that common point and this one, right? And this common point need not to be 0 all the time. Okay, so in the next video we will do some examples related to this improper integral type 1.